tens of descriptors fast, and it names just the right caches so you can avoid barriers that cost you a bunch of performance. It's great. Like you can write the fastest possible code with simple abstractions like this. So I said something about single-threaded data races, and this is a fun, compressed widget within the memory model of NVIDIA that I can explain quickly. There's quite a few of these sorts of things, but recently they added proxies. So I've got a program here. Maybe laser pointing will work. Yeah. Right, so I've got a program here, and I've got one object. The object is mapped into global memory. It's got like an address somewhere out in DRAM, and there's physical DRAM cells that store the data. And I can write a program to store to that location. Right, I just store some value there. But this is a GPU, so it's got loads and stores because you can program it generically. But it's also got graphics things like surfaces and textures. So I can go and load this data as a texture. Textures, it's not that useful to say, offset 1, offset 2. You sort of want to say, in this coordinate space, give me roughly the pixel around 0.3, 4.26. So you do like floating point indexing into these surfaces. So when these two things get cached, they exist in the same physical cache, but their addresses or how they're represented are different because textures have a different indexing mode to normal memory with regular loads and stores. So when you run this program, you can store to the surface, set the beginning of the surface to some value, and then you can load it as a texture. And if you've got stale data in your texture cache, it will just be incoherent. You'll just have a data race in your single-threaded program. But we added some tools to make life a bit better. There is a fence to combine the views of the world. I made pictures. Oh, I'm sorry. I'll skip through them. So here's the same sort of pre-execution. There's a program here with loads and stores like we've seen earlier and arrows for program order. And in the axiomatic model, and we're big fans of the axiomatic model, we say that PO union FR cycles, they're okay. You're allowed to see that. It's single-threaded data races, that's great, no problem. But we'll add proxy-preserved program order so you can get a sane view of the world. And the fences give you proxy-preserved program order. And we'll say that cycles in PPPO and FR are forbidden. So this is part of the NVIDIA memory model. It's a weird quirk. Other memory models, as best I know, don't have this. Just one of many exciting features that programmers, like I said, really like. I mean, they really like the features. They don't like thinking that much about it. So maybe they don't want to think about weak memory, but they do really want to write fast code. And we need to provide tools for programs to write the fastest code, and those tools are weak memory. So we want to think a bit about, and strategically within NVIDIA, we think about how we can use weak memory to help with NVIDIA's goals. There does have to be some guardrails, right? This is not gloves off, anything goes. That would be unusable. We wouldn't be able to write useful programs. We care about compositionality and portability. We also think hard about the consequences of what programmers ask us for. Sometimes they ask us for features that are non-compositional, that break some principle of cumulativity, for example. And we mostly try our best to resist that. Mostly we win. Like sort of as people inside NVIDIA making the case for well-structured, formally backed memory models. And we use formal axiomatic models to sort of check our homework. There's a bunch of papers that have a bunch of formalism in conferences that this audience probably recognizes. We care about making sure what we do makes sense in the general formal context. Why have we picked axiomatic models over something else? Why not have a big operational model that describes how the architecture works. We're architects, after all. You'd think it'd be nice to have an operational transition that says, clear this cache, or push this to that cache, or whatever. We don't find that particularly accommodating of future architectural changes. It bakes in an awful lot of detail about the way the machine works today, and flexibility with building future generations is nice. We're not concerned with having much more complicated models that deal with something like the out of thin air problem. We don't need something like promising semantics or semantic dependency, not of our concern. It doesn't matter to us. If you think it should matter to us, prove us wrong. Happy to hear counterexamples. There's, apart from proxies, a bunch of weaker still features going into the programming model, or in the programming model. From a given thread inside an SM, you can now spawn other threads that will do something. Copying data is like some DMA type thing. And then you can synchronize on it being done. And you can have a bunch of these working, all in parallel, at least from the programmer's perspective. With lots of features like this that are all communicating and all going fast, strong memory models are effectively impossible for us. So, at the crux of it, we want really weak features because they're fast, we can build them, and it's important for performance. We need to write code that multiplies matrices faster than anyone else's code that multiplies matrices. There is a principle of backwards compatibility that's important. There's a bunch of GPUs that are already out there, and we don't want code built tomorrow to not run on millions of GPUs that have already been sold. That's no good for anyone, including NVIDIA. We want to make it so that programmers can be effective even when they are writing fast code. So there are some guardrails like cumulativity. And we want it to be possible to reason about code using tooling. One of the consequences of building the most complicated axiomatic model is that, you still have to think about it, and the capacity of a human brain to think about these memory models is finite. Tooling helps a lot. So things like herd, or building the formalisms in Alloy, doing model checking are all useful things. To that end, we have some tools internally. I think this has been released, at least the code is out there as an artifact publicly. I don't know if you can easily run it. Like NVLitmus, where you can write a program in CUDA. It will compile it to ptex and then apply the ptex memory model on it and tell you if you've got data races, or if particular outcomes or assertions will fail because the memory model says there's some reorderings that are permitted. We don't really care about DRFSC. No one seems to want to write SC code. We're happy with release, acquire, and weaker. We do care about maintaining backwards compatibility, so we use formalism to prove that our memory model changes are strict extensions. So go ahead.
I just have a question about that. Do you not care about DRFSC, or is it that people only care about, you still want semantics that are SC for your programs, you just use release acquire only to get that?
Yes and no. Programmers aren't saying, we have never been asked by...
You want a sequence that doesn't vet, basically.
Right. Yeah, so no one writes membar SC because it's really slow. And none of our programmers have ever asked, can I rely on DRFSC? It's just not terms that they're thinking about writing programmers in. It might be because it's an unwritten assumption, but they don't appear to care. No programmer has looked at our DRFSC proof and said, thanks, that was great. Apart from satisfying an audience like this, mostly wasted effort, it appears. And the many hours in Coq that grad students have spent on the same task, maybe also wasted effort. And to that end, right, the effort we could spend on sharing the most up-to-date memory model and keeping it evergreen, or on providing proofs of every change, publicly, formally verified, machine checked. The ability for us to do that is finite. It's very nice if there's a permanent repository of all memory models. That would be great, but it does take a bunch of effort. And we've got to prioritize the limited effort we have on problems that matter to us. We've got some people who do this. There's not that many people in the world who know about this. The majority are in this room. It's tricky, right? We've got limited resources. We have to solve our problems internally first because we're thinking about developing future products. We can't do that out in the open for various good reasons. One is competitiveness. The other is just we don't want to promise a thing that actually we find out is bad and waste everyone's time. Programmers, academics, and similar. We're doing our best. One of the major tasks of building a memory model is translating English to English, right? We've got a bunch of different communities who need to be able to talk about weak memory, who use different languages. Architects aren't saying anything about building transitive happens before, right? They're talking about cumulativity and cache flushes and what morally strong is. Programmers are thinking about the rules of C++ and assuming the compiler will sort of do the right thing. Compiler writers are thinking about how they can best optimize some code and output some LLVM that makes sense, or output some ptext that makes sense, right? So one of the reasons that the memory model has value at all for NVIDIA is as an oracle for us to be able to translate from one language to another and say, this might not work because it disagrees, or this does work because it agrees. We know that writing informal prose is no good. You end up with technical documents that don't allow you to answer questions. But you do still have to write some, because you can't just put a bunch of relational algebra on the desk of an architect and say, build it. They'll go, no, I've built this thing. You can tell me if it's right or not. Our goals are to build a chip that itself is fast and can be programmed with fast code, right? And the memory model is the formal memory model is a means to that end. We don't particularly care that it's the most beautiful thing, and we don't even necessarily care that every proof is dotted off. We've got to make a product and make forward progress on that, and the memory model helps us, and it helps our users write useful code. But building a beautiful memory model is not a goal on its own. So, yeah, to conclude, we build a really weak memory model. We find programmers like it, not necessarily because they're into memory models, because they're into writing fast code, and this is the recipe to do it. We need the GPU to be a place where you can write fast code, where it continues working over time, and you can run it on a future generation and get at least correct behavior, perhaps faster code, and you can keep that same code around for a long time. We do use formal methods, and we write the formal memory model, but like I said, it's a means to an end. It's the tool we use to help us check our homework and help us develop a product that is useful. We're not doing it for academic insight. It is useful, however, for us to pay attention to what's happening in the community. Anyone who's using memory models who does sort of a paper and they base it on TSO or something, that's cool, but maybe misses a bunch of detail. Like if you're going to use an axiomatic model as your case study in a paper and you can use something more complex than TSO, that's good for us, right? If you can use then we get an idea of how your academic work can scale to the kind of complexity that matters to us. If you can use ptext, it's obviously much more direct. Yeah, that was my ramble. Thanks very much for listening.
I want to make the case for why you should care about out of thin air. So you didn't mention a lot that you cared about programs actually doing the right thing, but at least on one slide you said something about tooling and formal methods where I think what you were saying there is you want to have tooling which tells you if the program does the right thing. But for program verification, we need memory models that don't suffer from out of thin air, because with out of thin air, even most basic kind of reasoning principles fail.
But
so how do you do any kind of, I know this program will do the right thing, assuming the hardware implements my model, given you have out of thin air on the model?
We build a hardware model, right? We don't have compiler optimizations that are working against us like they are in a C++ model. We don't have to worry about dependencies being eliminated, mostly.
So you're not verifying the code you're writing, you're verifying the code that's output.
Yeah, so NV-litmus, it will compile it to ptex and then check the assertions in the ptex. If the compiler has deleted some dependencies because it's made some choices, well, that's in the realm of programming language memory models, C++ and CUDA, which inherits the C++ model near enough.
Okay, well, that means you need to re-verify anytime you update the compiler or anything like that. You're kind of, okay.
Yeah.
And it's completely non-compositional.
Yeah.
Okay.
We build hardware. We don't build C++. Right? We have.
You want people to write software for you, huh?
Yeah, sure, but we want people to be able to do that in general. We're not saying don't solve this problem. We're saying it doesn't matter that much to us beyond you have to be able to trust that compilers work at some point, right? It's good if that problem is solved, but it's not in the remit of NVIDIA to fix C++.
But doesn't NVIDIA build CUDA?
Yes, which has to have the same model as C++ so it can interact nicely with it.
So I love this talk, as you might expect, given my talk. I was kind of curious. So you're using the memory model as a design tool, or like as a sort of like as a kind of tool for kind of design consensus, I suppose. It sounds like, something like that. And I'm curious, like you were like, well, okay, it'd be good if this community keeps on doing stuff, but like what stuff is actually useful for you? If like, what is the hard problem you wake up in the middle of the night and you're like, oh God, I wish we could solve that. And then someone smart in here could, if they could solve it, would make all your lives way easier.
The problem that's keeping me up at the night at the moment is forward progress.
Say that again?
Forward progress. Liveness type properties, knowing that threads will eventually communicate with each other and how that interacts with scheduling.
And that's a memory model property?
It's adjacent.
Okay.
I'm unconvinced if it's separable.
How are you going, Matt?
So I just want to understand. So in the GPUs also, relaxed write, the lazy relaxed write is important for performance reason, or do you use it?
Yes, a lot, and it's very important.
Okay, so if you compile relaxed write into release write in, do you have release write kind of thing in the instruction? Okay, so then that's a problematic.
Yeah, that would be slow and unacceptable.
So somehow it's counterintuitive because GPUs are mostly data parallel computation, and then this synchronization or race thing should not be a big deal. But that's my intuition. But somehow what you're saying is
being able to hide the latency of the memory system is very important. Because it's very wide, memory latencies can be quite high. By being able to do reordering of relaxed as early as possible, we can hide a bunch of that latency, and it improves performance a lot.
Okay, but you maybe I can ask more details later. But